record to the cloud. Okay, so sorry guys, I just lost 15 minutes, but I'll go quickly through the first stuff. So just a standard warning that this lecture is being recorded, so you may want to turn off your webcam if you do not wish to appear in the recording. Also, you should note that somehow you have like 2 angles on me, so I don't really know, but this feels like a very Hollywood Zoom session. Just a little bit about me very quickly. So I did a PhD in Canada at the University of Western Ontario in computer science. I have a master's in pure mathematics from Simon Fraser University and a bachelor's degree in pure mathematics from McMaster University. So let me be proof that you can actually make a lateral move from pure mathematics into computer science. I really had no problem. In fact, I had huge benefits. They said, oh, you don't have to take your comprehensive exams because you've come from math, we trust, and that you know all the background stuff. So they actually, allowed me to skip a bunch of stuff. So I almost had an advantage coming in from mathematics. I just want to demo to you Maple. So Maple is a commercial computer algebra system that I basically worked for throughout my entire academic career. So as soon as I started a master's degree, all of the work that I was doing was like specifically with the intent of getting it into the Maple system. So this is kind of a weird company in that most of the serious development of the company is happening in the academy through labs that they sponsor. So I had to sort of split my time between the university lab and the company itself. But while I was at the company, it was nice to be sort of surrounded by other mathematicians. Like I was in the math department, so there is indeed places where you can get employed, like as a mathematician. So I just want to show you the product itself. So this is a Maple session. I reverted it back to the mode that I prefer. There's a lot fancier 2D type of stuff, but I'm old school. I like typing it in like this. So just to give you some idea of like the core functionality here. I may snap. Did we lose Zoom? Zoom, are you still with us? Okay, sorry, this is the most difficulty I've ever had with a Zoom meeting. Okay, anyways. Okay, Jesus, Murphy. If we make it to the end of this, it's going to be a miracle. Okay, so this is Maple. I just inserted some generic commands in here. Let's just ignore the fact that the projectors are toggling on and off at random. So what I can do here, so that's just a random polynomial, and I divided it by another polynomial. So right out of the gates, right, you can sort of have arithmetic on polynomials. And this is something that you're going to be dealing with quite closely in your project. I can take derivatives of polynomials, which actually is crazy simple. You just have to tell Maple like what the 3 rules of derivatives are. You'd be very surprised how simple the derivative command is. I could do things like expand this derivative. I can throw it at this simplify, which sort of simplifies it. So this really is a tool for sort of mathematicians and scientists who need to do sort of analytical type of approaches. It's not always the case that numerical solutions are going to suffice to things. So if you want to do things exactly, you're going to be working in this system. Things that you're certainly not going to see in numerical systems are commands like this, like give me the actual symbolic integral of this function, which is there. And then I can show you all the flashy bells and whistles. So I can plot. So those are the derivative, the antiderivative, and it's the function itself. And now we've lost every single projector in the room. So maybe everyone can just stand behind me. I don't know. Oh, so Zoom, like we're in a room and all the projectors are turning on and off, seemingly at random, just to spite me somehow. But I'll forge on. Anyways, so here are all the bells and whistles that marketing usually likes to pull out of the bag when we're showing Maple to new people. Although, sort of mathematically speaking, these are not the most interesting things, the plotting software. But in any case, we can get nice 3D plots. Let me just constrain the scaling here. Right? So you can get something that looks like a ripple. I can plot paraboloid very nicely. And you can see there's lighting that's coming into here, which is pretty neat. We can also get plot animations. So this itself is not yet interesting, but perhaps this is interesting. Right? The fact that I can Oh, actually, I'm supposed to, yeah, make this go back and forth. Yeah, see those oohs and ahs? Like, this is marketing salivating, right? This is what they want to generate, this type of... This is supposed to loop. There we go. All right, so there's the paraboloid with different parameters. This is going to look a lot less nice than the ones I generated here, but there's a difference between plotting like actual functions, like z is equal to f by x, rather than plotting something we call like implicit functions. So usually when you're plotting a function, at least one of the parameters is like linear. If you want to plot something like this, it's a little bit more complicated. We can still do it. It just looks a lot more sort of not as smooth, right? But I can always instruct the system to generate this more smooth. The person who had the desk beside me when I was in graduate school generated this graph theory package, so I feel that I have to show you it. It was one of the first graph theory packages that did plotting automatically. So normally what you do when you generate a plot and you want to view it is you just sort of put all the nodes at the vertexes of a polygon, right, and then connect them. What my colleague did was instead he sort of took all the nodes and connected them with springs, or sort of mathematical springs, then perturb the system a bit, and then the graphs find a natural steady state. And they're a lot more visually pleasing to look at. So you can get something like this, which is the Peterson's graph. I'm not sure that was actually developed with perturbation, but we got pretty interesting things. Now, what I'm going to show you now is the stuff that I am interested in, and what the sort of not last 8 years, but the 8 years I spent studying postgrad was sort of dedicated to the following lines. Okay, so first of all, I was very concerned about polynomial arithmetic. We're going to learn that arithmetic is the bread and butter of a polynomial, of a computer algebra system. So manipulating them, expanding them, simplifying them, evaluating them, this is all quite important. So I have a polynomial here, f. I'm just going to expand it. But you can see that what the roots are, right? 1 is a root of this polynomial. Square root of 3 is a solution to this polynomial. And a cubed root of 5 is a solution to this polynomial. So what do you expect to come out of this solve routine? Right? If you gave this to MATLAB, you would say, oh, I'm expecting to get numerical approximations to all of these roots. But this isn't a numerical system. This is an exact system. So anyone have any guesses of what we can expect to see come out of, if I hit solve here, what would be a sensible encoding of exact roots? Well, this is sort of the crux of computer algebra. This is what it shows you, right? And I bet you numerical systems don't show you this because they can't, right? This is saying one of the solutions is 1, another one is the square root of 3, another one is minus square root of 3, the third root of 5, and it's also picking up all of these complex roots. That's what that capital I is. But these are exact solutions to that function or that polynomial. So this is quite important, the fact that we can report things back like this. A big part of your project, actually the whole target of your project, is to get to a point where you can start factoring polynomials. Now, why is factoring polynomials interesting? Well, how do you think solve solved that f? It just factored it. And once it's factored, you have a list of irreducible components which should be encoding the solutions to this function f, right? Here's the first one, 1. Right? Here's the second one, and there's the third one. Right? So in some sense, factoring polynomials is what we consider solving polynomials in an exact system, right? Which is pretty important, right? So I just want to, when you're looking at your project, know that you're, first of all, implementing something that's not extremely trivial. Like you're going to implement a fairly modern algorithm for factoring, but you should know factoring is more important than just sort of separating into factors. You are solving the system exactly, and that's a big deal. We can do things sort of bigger. So here's a bigger polynomial. In particular, you will be factoring over a residue class. You can't divide polynomials in their natural state. Right? It's like if you have an integer and another integer, and you divide them, you may generate a rational. Right, so the integers aren't a field, right? A field being a ring where every element has a multiplicative inverse. So how we're going to rectify this is I'm going to say we're going to restrict our coefficients of our polynomials to be over a field. And that field is going to be like Z mod 3, Z mod 7, Z mod 11. And I'm going to talk about all of this number theory on Monday and Tuesday, right? So this is just sort of like the very high level view. So don't start panicking. We're going to go through all of this stuff in a lot of detail. But you should be able to factor f mod 7. And there you go. So these are all the solutions to f, exact solutions, mod 7, right? Because we factored them. So, you know, mod 7, are there any linear factors in here? Yeah, 0. 0 actually is going to be a solution to this function mod 7. So there's a couple quadratic roots here. Something else that I'm interested in doing, but it's not going to sort of be involved in your project, is like solving multiple things, right? Solving systems of polynomials. Where do polynomials, if I give you two polynomials and we draw them, where on that plane do these polynomials cross one another? And that's what sort of this solver is solving. This is kind of weird. It's saying, oh, the solutions to f and g are the roots of z squared minus 3. So it's saying your solutions are plus minus cubed root of 3. So this is important, right? What is the fundamental object of a computer algebra system? Well, we can say the fundamental object of something like MATLAB is the float, right? Everything comes down to manipulating floats. The fundamental object of a computer algebra system is the polynomial. Why? Well, if you think what we have to do is we have to extend our numbers to capture all the numbers floats can capture without actually using floats. So we can get integers. Okay, that's great. We can get rationals, fractions. What numbers are we missing? What numbers aren't rational? This is a slow ball of all slow balls. Irrational numbers, right? So what are special about irrational numbers? Well, at least the algebraic ones. Have you guys ever dealt with algebraic numbers? Does anyone recall the definition of an algebraic number? An algebraic number is the root of a polynomial with integer coefficients. An algebraic number is the root of some polynomial with integer coefficients. Like square root of 2 is an algebraic number because that's the root of x squared minus 2. If you put square root of 2 into that, you get 0. So really, all the algebraic numbers, right? When we're talking about numbers, what we're really talking about, how do we choose to codify them or encode them in the computer? And I'm saying we're going to choose to encode numbers by just manipulating polynomials. We don't really have the number 1. We have the root of x minus 1. We don't really have the number root 2. We have the root of x squared minus 2. Right? So manipulating polynomials can be regarded as equivalent to manipulating numbers. Right? Numbers that can include integers, rationals, all the way up to algebraic numbers, which are things like the square root of 1 plus the cubed root of 3 plus the 7th root of 7. You don't get things like e or pi, but like no system gets things like e or pi. I'm much more likely to get pi into a symbolic system than I am to get it into a numerical system, because pi, it's not really a number, right? A lot of these constants we have are just defined by the properties that they have. What is pi? Well, it's the circumference of the unit circle, right? That's something I can explain to a computer, right? All other systems have to take some sort of type of finite approximation of them. So in any case, you're also going to implement this GCD operation, which tells you sort of what common factors do two polynomials have. And what common factors do two polynomials have? Well, their common factor actually is telling you what their common solutions are. So the common factor between f and g here is x squared minus 3. So actually they share the roots plus minus root 3, which is the thing that is being stated one above. Right? So I'm showing you this just to emphasize the fact that GCDs and factoring, right, are more than just GCDs and factoring. They're also solving singular polynomials and solving systems of polynomials. Okay, so I'm going to move out of this sheet, and we're done with this Maple demo. So I'm going to talk more about computer algebra, just fleshing out some of the things that we've talked about. I'm sorry if I'm going fast, but I lost 15 minutes, so I have to move through. So before I tell you what symbolic computation is, or computer algebra, or exact computation, let me tell you what it isn't. It isn't numerical computation. And I sort of have to say, you know what, for like most scientific applications, engineering, like numerical computation is more than sufficient. You only need 15 digits of pi to navigate the space, right? I think 39 digits is adequate to estimate the volume of the known universe, accurate to within a hydrogen nucleus. So I'm not pretending that the stuff that I'm doing is going to be, you know, mind-breaking or really going to advance engineering and science that much. But pure mathematicians need tools too, right? People who need like analytic solutions need tools too. So like the celestial mechanics, algebra. So there is utility for doing this. And there is some stuff that we can solve that the numerical people can't solve yet, right? Because they have to be very concerned about numerical instability. Have you learned at all about numerical instability yet? Yeah, but like, why is there a floating point error? But is that like intrinsically bad? That like it's an approximation? So here's the problem. The problem isn't, let me skip this one because we talked to, well, okay, I'll talk about this, then I'll answer the question. You're very close. So one thing that a numerical system can never do is represent an algebraic number, which I said was very sort of straightforward if you just let it be the root of a polynomial. Take the square root of 2 with any system that you want, right? Here it is to 10 decimals, 15 decimals, 20 decimals, and square it. You're never going to get 2 back. Ah, but professor, that last one is 2. Well, no, it's 2 with a bunch of zeros, but you're actually uncertain what the next thing is, right? So you're never really going to generate 2 back. And given that the square root of 2 has one property, and that is if you square me, you should get 2 back, right? This is a problem. So we are sort of immediately approximating things, but that itself isn't too much of a problem. The problem is the accumulation of these errors, like while you do arithmetic. So if you have 2 numbers with some error in them, and then you add those 2 numbers, right, then you have double the error. So it's like if you're saying my answer falls in this interval and the other answer falls in this interval, add them. Well, now the interval is twice as wide, and that's going to keep happening as you keep doing additions. This is a disaster because mostly what we're concerned about numerical solving is solving linear systems. And Gaussian elimination, all that is like a ton of adding stuff together. Right? So if you ever take a numerical analysis course, they're going to be deeply concerned about keeping the stability of numerics under control when doing linear algebra. Multiplying is a little bit better because a tiny number squared is going to be even tinier. So like this sort of disappears. But this does double something called the relative error, right? How close you are as a proportion to like the exact measurement. So both adding and multiplying is just going to keep introducing more error and more error into your system. And you're always going to have to keep this under check by playing tricks. So in symbolic computation, the first thing that we need is a provision to just have integers that are like arbitrarily big, which is not a problem. I think you may have actually learned some techniques for letting integers be arbitrarily big. The fact that we can have rationals is already a big deal, right? 1/3 is already a number that numerical systems can't cope with. And arithmetic on polynomials, which I'm saying is like the most important atomic operation of a computer algebra system. Okay, so why don't we always do symbolic computation if it's sort of better than numerics? Well, numerics is faster for one, but we create a different problem by ignoring floats. And that is, we have to start dealing with rational numbers that are preposterously big, right? Like 600 digits numerator, 1,000 digits denominator, if I really want exact precision on anything that we're computing. And that's going to become a problem as well, especially if you want to start reducing your fraction, because you're going to need to do so many GCD operations. Okay, we've solved this problem in computer algebra by saying, well, maybe we don't have to do the problem over the integers. Maybe we can do it over something easier. So that's what we're going to do. We're going to work over ZP. We're not going to use all of the integers. We're going to use like a finite proportion of them and one that has a prime number of elements. Like we can say, okay, screw having all the integers. Let's use 0 through 6. We're working mod 7. We actually have techniques where we can find the answer over various prime mods. I can find the answer mod 7, mod 11, mod 13, mod 23. And eventually I'll have so many of them that I can reassemble those images to what it would be mod Z. Has anyone taken any number theory here? Did they teach you the Chinese remainder theorem? This is exactly what we use to lift. Okay, so we have two techniques, Chinese remainder theorem and p-adic lifting. Chinese remainder theorem, I have a slide for this. P-adic lifting is, suppose you want to like write a base 10 number and you want to switch the base, right? So any number can sort of choose a base. Any number can be written as something times base to the 0 plus something times base 1 plus something times base squared, right? So you do that with 2, you get the binary numbers. You do that with decimals, you get, 101 is 1 times 10 to the 0 plus 0 times 10 plus 1 times 10 squared. Okay? If I replace that 10 with a p like prime, I can sort of find something mod p, and then mod p plus p squared, mod p plus p squared plus p cubed, and that's called p-adic lifting, right? So that's taking some solution that you found, mod p, and you get to keep lifting it up until eventually you have the solution mod z. We're not going to learn that. That gets a little bit tricky. I'd have to teach you a lot of stuff about Taylor series, but Chinese remainder theorem is not too bad. So here it is in two sort of integers. If you give me p and q and they're coprime, and you tell me what their remainders are, mod p and mod q. Oh, sorry. You give me p and q and they're coprime. Let's also call them primes, so they're automatically coprime. If you give me two integers a and b, and you tell me what the remainder of a is mod p and the remainder of b, hold on. Did I screw this up? Let me just read through this properly. Let p and q be coprime positive integers. Yes. And let a and b be arbitrary integers. Okay. Then there is unique n such that a is equal to the remainder of n mod p and b is equal to the remainder of n mod q. Okay, so what this means, do you guys know how to do mods? You know how to take a remainder? So if I say 11 mod 5, what's that? 1, right? Because you can remove 5 twice and you have 1 left. So all I'm saying is if you give me a number and you tell me what that number is, if you take the remainder mod p and the remainder mod m, I am able to reconstruct the number, the original number. It's like the larger number that will give me n in both cases. So for example, I don't have an example here, but working over prime residue classes allows us to ignore the fact we're working with fractions. Now, why can we ignore the fact we're working with fractions? Well, consider that a over b is the same thing as a times b inverse. And everything in a field is invertible. Right? So not only can we take solutions to smaller problems and lift them into the larger class, like integers, we also eliminate the need for fractions, which is also quite great. Okay, so here's how we could sort of use this. You are going to have to actually implement a smarter polynomial multiplication algorithm. I think you have two choices, either interpolation or this Chinese remaindering technique. So I may say, here's f and here's g. I want to multiply them together, and I tell you that their product is this mod 7, is this mod 11. And eventually you do so many that you have enough to use Chinese remainder theorem to give the answer over all of the integers, right? So this sort of helps us avoid working with arbitrarily large integers, which becomes problematic. There are other techniques which are surprising. So if you want to multiply two polynomials together, it's actually faster to evaluate them individually and then multiply their evaluation points. What does that give you? Well, it's actually giving you evaluations of the product. And if I get enough evaluations of the product, you can interpolate through those set of points. And that ends up being faster, right, than a generic multiplication algorithm. Don't forget that if I give you 3 points on the plane, there's a unique parabola that goes through those 3 points. If I give you 4 points, there's a unique cubic, and so on and so forth. Right? So if you have a polynomial of degree 3 and a polynomial of degree 2, and I give you 5 evaluation points, is it 5? 6 evaluation points, you will be able to interpolate the unique quintic that goes through those 6 points, which will have to be the product of those 2 polynomials. So this is one of the other options for your project. I'll teach you how to do interpolation. Okay, so I'm saying that polynomials are basically what we're using to encode numbers. So the natural question then becomes, how do we then evaluate with algebraic numbers if these things are trapped as polynomials? Remainder has this funny property. Did anyone ever teach you this trick about synthetic division in high school? If you ever have a polynomial and you need to do a polynomial division, and what you're dividing out by is linear, you don't actually have to do anything. If I take x cubed minus 2x plus 2 and I divide out x minus 3, you just have to evaluate f at 3. That's all it does. Right, so this was a really handy trick back in high school because I could get the evaluation points instantly. Not only is that a handy trick, it's generically true. Right? If I take a polynomial f and I take its remainder modulo g, what that is equivalent to is evaluating f at all of the roots of g simultaneously, kind of. So the second one here, if I'm saying, how can I say evaluate the square root of, take the square root of 2 squared? Then I say, oh, okay, just take x squared and divide out x squared minus 2, right? And what the result of that, it's going to evaluate the roots of x squared minus 2 in the original polynomial. So that's going to give you 2. So that's how that exact calculation works. Again, because we're not doing arithmetic on numbers, we're doing arithmetic on polynomials, where everything is just sort of evaluating by roots. We can even get the complex numbers out of this, right? Because the complex numbers, is just sort of like a special algebraic number, right? The complex number is the algebraic number corresponding to x squared plus 1, right? The roots of x squared plus 1 are plus minus I, right? So x squared evaluated at the roots of x squared plus 1 should give you minus 1, right? Plus minus I. So I'm just going to walk you through very quickly the development of computer algebra systems since their inception, because it's a fairly new discipline, and all of software is fairly new. You don't have to go too far back to the creation of the computer, right? So we really have to start back in the 1950s. So this is sort of the basic canonical example of the differences between numerical and symbolic software, but let's do something a little bit more complicated, less trivial. Suppose I want to have a computer system work with Chebyshev polynomials. This is a polynomial given by that recursive equation. So it's basically 2x times the previous Chebyshev polynomial minus the previous Chebyshev polynomial. So there you see them down across the bottom, 1x, 2x squared minus 1, 4x cubed minus 3x. So what was one of the first proper software languages that had utility in scientific computation? Has anyone ever worked with, has anyone ever worked with Fortran? Okay, so Fortran, or Formula Translator, was one of the first real computer languages that had wide usage. Now, this can't represent a Chebyshev polynomial. The best that Fortran can do is say, if you give me x, I can tell you what the Chebyshev polynomial evaluates to at x. But I can't tell you what the Chebyshev polynomial is. Okay, so that's 1958. 1968, they extended Fortran to Altran. And this did give a provision for saying, oh no, now you can properly work with symbols, right? So here are the Chebyshev polynomials across the bottom. And so this really is the first instance where symbols start coming into play. So we're going to go from the 1950s till now. I'll just tell you about all of the systems that have been developed. I'll just read this. I don't even know if this comic exists anymore, but he's just cutting out Fortran snippets, putting them in Fortran cookies and calling them Fortran cookies, which I think is funny as a dad. Okay, Lisp processing. This actually still exists. It's considered sort of one of the first computer algebra systems by accident, right? We sort of accidentally, because we moved from this infix notation to Polish prefix notation, somehow for free you get a polynomial arithmetic out of this. So we almost get it by accident. And that's John McCarthy there at MIT on the left. 61 through 65, MIT writes Saint. It's pretty good at doing calculus. It is about as good as an undergraduate calculus student. 64, Formac at IBM. PM, polynomial manipulation in 65 at IBM. A lot of this stuff was done at IBM. I know a lot of these professors who worked there. In 1965, Math Lab was created, not to be mistaken with MATLAB. This had a lot of the modern features in it, like factorization and differentiation, Laplace transforms, solving like ordinary differential equations, matrix inversion. In 1966, we held the first international conference for computer algebra. This is how you're starting to know that you're starting to make it, when you can sort of assemble the Avengers all to one place to talk about a subject discipline. This was held in Washington. In 67, SIGN was created, Symbolic Integrator at MIT. This is for symbolically integrating, which was one of the topics that we thought we might give you, but in all honesty, it's not that interesting. Symbolic integration, we just take whatever you give us, make a really long partial fraction expansion, find all the integrals because they're all going to be lns of something and special functions, and then come back in. But in any case, that's what they did in 67. Reduce is still fairly popular. This was created at Stanford. There's the original paper talking about it. Here are all the guys who made this stuff. The fellow who I labeled with Reduce made Reduce. A grumpy-looking fellow at the front created Lisp. I'm not sure if they're still alive or dead, but a lot of these people exist. I'm trying to... It's fun working with modern technology, because after studying math, where like everyone's been long dead for centuries, you start studying math created by people who are alive. And this is it's a revelation when you get to that point where you're actually studying modern mathematics instead of the historical one. Okay, so we get more stuff through the 60s to 70s, MIT, Altran, just more people trying to outdo one another. Camel is still quite popular. This one was tailor-made for doing celestial mechanics, like orbital mechanics, right? The planets spinning around one another and stuff like that. Those are the papers there. Reduce 2 and Scratchpad, also very popular. I know I'm going quick, but I'm just trying to recover those times. Maxima was pretty ambitious when they came out with it. So what they introduced was limit calculations, that's fairly complicated to determine what the limit of something is. And now they're already talking about introducing lifting, right? Utilizing the fact that we can compute the solutions to some of these problems in smaller residue classes and bring them up. In 1971, they held the second one in Los Angeles. And 1980 at Waterloo. So this is sort of when I start coming into play. Waterloo is a university in Canada. It's one of the best universities in Canada, and it's one of the best universities for mathematics in the world. And in 1980, they wanted to buy Maxima, but they couldn't afford it. Or I guess they couldn't afford either the software or the computer that it ran on. So what they decided to do is just write their own system. And we'll get back to what that system was. Let's skip over the 80s. So the 80s hit, and everyone wants to be making money. So this is where the commercialization of computer algebra systems starts coming into play. Probably none of you have used Maple, but some of you have used Wolfram, Mathematica? Yeah. So both very similar systems. We sort of have a friendly competition between one another. So here's Mathematica. It's one of the first systems developed in C to do symbolic computation. You can see its interactive environment there. I think, who knows who this person is at the podium? Yeah. It's Stephen Wolfram. I took this picture. So that's my master supervisor on the left, Michael Monaghan. You'll notice that I said we're using his notes. So I actually met Stephen Wolfram. This is at the Isaac conference. He's a brilliant, brilliant man, but kind of grumpy. He quits college because he found it boring and awful, and he received a PhD in particle physics from Caltech. And notably, his thesis committee included Richard Feynman, which I thought is just like exceedingly cool. Like Richard Feynman's like my hero. So he then went on to create Wolfram. I'm sure you've used Wolfram Alpha and stuff like that. All the technology is very similar. We're all using the same algorithms. We just have different implementations of them. This is Maple. So this is the thing that came out of that group that couldn't afford Maxima. They created their own symbolic computation package that ended up being better than the thing that they were going to buy. So this was developed by the Symbolic Computation Group, which SEG was the former lab that I was involved with. And when this came out, its major feature was the fact that it could just have integers as large as you want, right? We will fill up your memory to store integers, but you can indeed have ones as big as you would like. That's Keith Geddes. He is the nicest guy. I got very drunk in his backyard before. But he wrote that textbook, Algorithms for Computer Algebra, which contain many, if not all, of the fundamental algorithms for doing computer algebra. He's a Canadian. He studied at the University of Toronto, which is where I was teaching before this. He also did it with his partner in math, not in romance, Gaston Gonnet, which you may not know this, but the University of Waterloo is actually responsible for digitizing the dictionary. Right, so Gaston Gonnet and I believe one of the Borwein brothers. Well, you have to figure someone had to be the first person to do X, right? So this is just a neat thing that he can say he digitized the Oxford English Dictionary. So Gaston and Keith won a huge award, well-deserved. They're both retired now. I'd be remiss not to mention that there is a locally grown computer algebra system called Magma, which is actually pretty competitive. It's pretty fast, but somehow it's not as widely used because it's quite expensive. Although I don't know if this is still true. At one point, the distribution of the software was underwritten by the Simmons Foundation, so universities had this for free. So you can go check it out. The fellow who maintains this is also quite nice. I've traveled with him, just his name escapes me. The rise of the special purpose computer algebra system. So that's sort of what happened after the commercialization, was researchers decided that there's no way they can compete with an entire company, but perhaps they could carve out some tiny niche and optimize something. So we have Cayley, that's like specifically for group theory, Form, high energy physics, Lie for Lie algebras. Have you guys dealt with Lie algebras yet? It's like matrix multiplication on steroids, right? It's the worst. Macaulay, that's the kind of stuff that I'm interested in, these Grosvenor-Basis calculations, and Perry for number theory. Just be aware, if you need to do a very specific thing, there's probably a computer algebra system that was made to optimize against. The modern era, so all we have now is sort of these open source computer algebra systems. William Stein from the University of Washington has this Sage. Have you heard of Sage? It's fairly full-featured for something that's free and open source, so you can take a look at that. Python has something called SymPy. I've never used it, but perhaps I'll start taking a look at it. And then actually MATLAB is now getting on the Symbolic train. They interviewed me to work there, but my German was non-existent, so that was kind of a deal breaker for them. So if any of you guys want to learn German and computer algebra, I can send you to go work with the guys in, where is it, Stuttgart? Okay, so what was my part in this? I'll take the next 10 minutes maybe. I know I'm going over time. So I am very interested in solving systems of equations. Right? When I was young and they showed us Gaussian elimination, my first question was, okay, so we can solve systems of linear equations, but like, how can we automate the solving of ones with squares and cubes? Like, I can do it by hand, but there doesn't seem to be like a systematic approach for solving these. I didn't learn the answer to that question until I was like in my mid-20s. That's how long, like that's how much math I had to learn to understand that, yes, Gaussian elimination does generalize, but it's not simple. It's not something that you can learn in high school. It's sort of like, you have an upper triangular form, and then sort of make that a cube instead, and you have some sort of upper triangular prism, and then you want to do that, unfold it again in the next dimension, in the next dimension. But in all cases, the goal is the same. You give me a set of equations, and I want to do a bunch of sort of manipulations or transformations on those equations so that the solution set of those equations doesn't change, but somehow like the thing I end up producing is a better representation of the solution. So it's easier to see this in the linear example. Right? There's a linear system on the left. There's an equivalent linear system on the right. And I hope you can see that like the solutions on the right are like way easier to construct than the ones on the left. Right? All that matters is the bottom one says, oh, z is d naught prime over c naught prime. And now I have z, and I can back substitute and work out y. And now I have y and z, and I can back substitute and work out x. This is going to be the objective in all cases. Right? I want to get some type of upper triangular form. So here's a system that's no longer linear, that has higher powers. And what we can do is make the same type of sort of solution-preserving transformations on that set of equations to get what's on the right. And what's important about the thing on the right? Well, the bottom equation is saying, here are your roots of x. I can take any of those roots of x and substitute it into there to get y. And I can take x and y now and substitute it into there and get z. Right? So that's what we really call a triangular form. Right? The triangular form is just sort of an assertion about, I need to be able to do back substitution, starting from one of the roots. Now, how do I get a root out of here? I don't care, right? Because for me, as a computer algebra designer, that's a number. There's your number. It's the algebraic number that goes into that. That's the solution to the equation. Now, scientists and engineers may be unsatisfied by that, which I would say, use whatever method you would like then to extract a root from this. Right? There are plenty at your disposal. Newton's iteration will give you arbitrary roots of this. Better yet, I want to do sort of like a factoring, right, of all of the roots, right? So still here, like these are higher degree. I can do more sort of solution-preserving operations to split the system further into these things. They're called triangular sets. And you can see that these triangular sets are fairly easy to read the solutions off of. Like this one, x is 0, y is 0, z is 1. That's just saying that that's one of your solutions. This one's more interesting, right? Because this is saying, well, one of your solutions is, like x has to be a root of this polynomial. It's going to be some algebraic number. And then y is equal to that. And then z is equal to that. Right? So factoring, the thing that you're going to be doing is like a fundamental operation for doing this kind of stuff. Right? So don't feel like we're trying to get you to do something like that's busy work. It's going to be a little bit tough. You're going to have to be very detail-oriented. But at the end of the day, you can sort of lie back and say, wow, like I really created something which is like the fundamental operation of like a computer algebra system. So you should feel very empowered after that. Okay, so what did I do? Well, just I'll tell you what I did, and then I'll send you guys home. So the package that allows you to do these type of factoring or solving is called regular chains. And my supervisor, when I was a PhD student, is the author of the regular chains package. So I was given something that we weren't yet able to resolve. So there's this theorem called Bézou's theorem. And it sort of is expressing something which may seem obvious, but is actually fairly complicated when you want to start working it out. If I say, here's a system of equations, like how many solutions can we expect to find? If I give you something like a parabola and a line, I think you can say, yeah, I expect to find 2 solutions. Right? The parabola is of degree 2, the line's of degree 1, the product of their degrees is 2. But obviously, you don't always get 2 solutions. So in the first picture here, there's 2 solutions. In the middle picture here, It intersects once, but this is sort of a special intersection. Why? It's tangent. So I kind of want to count that twice, because this is sort of special, that root. What about here? Are there no intersections here? You just can't see them. They're in the complex plane. Right? So I can't really draw that, right? But there's always going to be solutions to the parabola in the line, right? If you let me go to the appropriate space of numbers where they're going to be solved. So I had to sort of reconcile this case, right? What do we do in this case? Obviously, we want a statement like this, sort of like the number of solutions of a set of equations is sort of bounded by the product of their degrees. If we weight them, if I can say tangent intersections count a little bit more, then I can actually change that less than or equal to equal. And actually, I can make this very precise statement, which is now sort of going way too far, where the sum of the intersection multiplicities, which are the weights, is equal to the product of the degrees of the system that you're trying to solve. Where the intersection multiplicity is the vector dimension of this ideal localized at that space, right? So this is where I've lost you, but it's what I did, right? I managed to sort of explain to this system how to calculate the fact that that has a weighting of 2, but more than that, right? I obviously had to go to all dimensions. So here's another situation. If I give you a circle and an ellipse, these are both objects of total degree 2. I expect to find 4 solutions. There's one of them. There's another one. There's another one, but it's counted as 2, right? Again, because of this tangential intersection. So all I did was all I did was for 5 years develop an algorithm that could go and compute this efficiently and implement it. So you could give me this circle and an ellipse, and my software can report back that, yep, the solutions that are encoded by this piece have weighting 2. The solutions encoded by this piece have weighting 1. Yes, sir?
Isn't it just subtracting the 2 equations and finding the roots?
No. It's a lot more than that. Right. Well, for one, like you may only be thinking of the planar situation. Like this has to work in like all dimensions. You may not realize that the problem is this, right? You may like have curves that cross over themselves, right? So you've ever, like the Jesus fish, right? Its tangent space at its cross is not one line, it's 2 lines, right? So that's where things start getting complicated. You don't really have a tangent space, you have a tangent cone, right? You have it's a different type of linear approximation. So yeah, so you can get linear approximations that are planes, but those are fairly simple surfaces you're talking about. Surfaces can cross over themselves, at which point you gotta, it's now a cone, which is the linear approximation at that point rather than a plane. Yeah, I wish it was that easy. Then I probably wouldn't have wasted like 6 years of my life. But this is the, so that thing in pink up there, that algebraic geometry tools, that's what I wrote and implemented. So I just want to sort of convince you that you can be a mathematician and software engineer at the same time. Right? Like, I couldn't have implemented this without first devising all of the mathematics that made it possible. Right? All of my algorithms come with proofs certifying that the algorithm is actually computing the thing that it's supposed to. And that was the demand of the reviewers. Right? So I had to say, like, so there's this notion between constructional mathematics and existential mathematics. So I'm sure you've done a proof where you've proved something exists, right? Well, is that useful for actually constructing that thing? Like, what if I actually need it, right? Knowing that it exists is like, great. At least I'm ensured that if I search for it, that this is not going to be futile. But sometimes I actually want to know what that object is, right? So this is called constructional math, right? If you have a proof which actually builds something, that's the type of proofs that I'm interested in. I actually used to work in a lab called the the Center for Constructional and Experimental Mathematics, right? Where we were sort of, like, a lot of my dissertation was taking stuff that said, oh, well, let's prove it exists, and like actually having to come up with a constructive proof. Another thing that always happens in math is they say, we want to work locally at this point, so just make a linear shift to the origin. Shift this point to the origin, it makes all the math more clean. It's like, well, that's great theoretically that you can do that, but like doing this practically is a totally different story. So I had to rework all of the math like without doing this localization, like actually working at that point. Okay, so this is what my package does. So just in summary, symbolic computation, this is something that lies at the intersection of pure maths and computer science. So you can do both. Right? There is an option for you where you're not going to have to pick one or the other. In symbolic computation, the fundamental object is the polynomial rather than the float. And this eliminates numerical instability but requires that we can handle arbitrarily large integers, not floats. So next week, we're going to start talking about, I gave you a very high level view of what we're going to have to talk about in a lot more detail next week. So next week, we're going to have 3 hours together. I'm going to teach you the fundamentals of working in residue classes of prime characteristic. That is, how does arithmetic work if you only have 0 through 6, right? 7 numbers. Then we're going to talk a little bit about Chinese remaindering. I'm going to talk to you about how we're going to represent polynomials in Julia, how we're going to do arithmetic on polynomials in Julia, and then I'm going to show you the tool set, mathematical and algorithmic, for factoring. Like, you should go home and think. If I gave you a random polynomial and told you to find its roots, how would you do that? Like, you can find the integer, you can find the linear roots easy, right? You just start asking. Do you evaluate to 0 at f1, f2, f3? As soon as you find like f at p is 0, you know that x minus p is a root. Okay, you found all the linear ones. Well, how do you find the quadratic ones? You can't just start randomly guessing algebraic numbers, right? So think, right, of some way that you could factor a polynomial. I'll give you a hint. Suppose, like, we know how to factor integers, although that's sort of like computationally infeasible. But presume you can factor an integer. How could you use an integer factorization to build a factorization of a polynomial? There's sort of an obvious way to do it. And I'll show you come Monday. So I'm sorry I kept you for an extra 7 minutes. And you have a deficit of 7 minutes, so worst of both worlds. Is there any questions before I shut this all down? Okay, then I'll see you on Monday. Come caffeinated. We're going to need it. See you guys later. I'll hang around for a bit if anyone has any questions. I'll stop the share. I will stop the recording.